Welcome back. In today's video, we're going to talk a little bit about how to use the chain rule and apply it in the case of multivariable functions. So I'm actually going to do this just by explaining it through example, since it's kind of hard to give a formula or anything like that that applies in every scenario. So like I said, we're just going to work through some examples, and hopefully that'll kind of show how this all works out. So our first example that we're going to look at is f of x and y is equal to x cubed plus y squared. And we're going to suppose that, okay, so f is dependent on x and y, but let's suppose that x and y are also dependent on other things. In particular, x could be dependent on r squared times s, and y is dependent on s squared times t. And suppose that we want to find how f depends on r, s, and t. Or in particular, we want to find the partial of f with respect to r, partial of f with respect to s, and partial of f with respect to t. So the way that we're going to find these different partial derivatives is going to be to create kind of like a chain of dependencies between f and then to x and then to r, and then also similarly maybe through y down to r, and then same idea for s and for t. And the way that I like to kind of go through this is using kind of like a tree diagram that shows how all of these things are related to each other. So f of x, y is obviously dependent on x and y like so. But then x and y are each also dependent on things. X is dependent on r and s, and then y is dependent on s and t as well. I really like working with these diagrams because I think it kind of helps keep everything organized and stuff. So strongly encourage that you draw out one of these, and I'll show you how this works. So to be able to, I'm actually going to go ahead and start with df ds, I think, in this case. To be able to find the partial derivative with respect to s, we're going to do this by following the path from s, or from f all the way down to s, because we want to relate f to s. So we're going to follow all of these paths. And one way that we can think about each of these connections here is as another partial derivative. So like f is dependent on s, so a change in f had to come from a change in x. So partial with f with respect to partial of f with respect to x. Same idea between x and r. So partial with respect to x of x with respect to r, like so, is what this line could represent. And then this line right here says, okay, a change in x had to come from a change in s. So we can put dx ds here. And then similarly, df dy here, dy ds here, and then dy dt here. Okay, so these are all partial derivatives that correspond to each of these relationships. And if we want to find df ds, all we have to do is start at f and then make a path that goes down to s. Okay, and we actually want to find each path that goes down to f. So the first one we're going to start with, or that goes down to s, we're going to start here and then go down through x to s. And so what this means then is that we want to multiply things together that are in the same path. So df dx times dx ds. And then we also want to consider the dependency that passes through y. So we'll draw that path as well, like so. Okay, so this encompasses df dy and dy ds, so we're going to add that to our other path. So df dy gets multiplied by dy ds. Okay, so now all we have to do to find this partial derivative is just find each of these four partial derivatives and add them together, multiply them together, add them together, and then that's pretty much all there is to it. So start with df dx. This partial derivative, that just means we have to go back up here and take the partial of f with respect to x. That's just going to be 3x squared. Partial of x with respect to s means we look at this equation here, x dependent on r squared times s, and take this partial derivative. That's just going to give us r squared. And then similarly for this next term here, df dy, that's going to be equal to partial of f with respect to y, so 2y, and then partial with respect of y with respect to s. That's going to give us 2st. So all we have to do is plug each of these pieces into here, and then we're good to go. So df ds is equal to 3x squared times r squared, and then plus 2y, which goes with that df dy, times 2st. Okay, so now before we go too much farther, I want to point out that a lot of times we want to make sure that everything is in terms of the variables s and r or t or whatever. These are actually called your independent variables. So that's that bottom row. Basically, it just means that there's nothing that gets plugged into these guys. And typically we want our final answer to be entirely in terms of those independent variables. So that just means that we have to go back up to these equations here and plug those in. So we get like 3x squared is going to become r squared s squared times r squared, and then plus 2 times, and then that y is going to get replaced with s squared t times 2st. So we're going to substitute the independent variables. And then we can just simplify it down a little bit. So we get 3 r to the 6th s squared plus 4 s cubed t squared for this guy right here. And that's your final answer for df ds. So just to kind of recap what we've done here, we wrote this tree out and we went down and you always want to make sure you draw this tree. Anything that was on the same path got multiplied together. And then after that, you just add the paths together. Okay, so the df, dx, dx, ds came from following this path of dependency. We multiplied everything that was in that path, so that's going to be the df dx times dx ds. And then we looked for another path down to s. This one went through y, found those pieces, multiplied them together, and then added those two, the stuff that came from those two paths together there to get all of df ds. Okay, let's apply this same idea to get, let's see here, what's next? df dr. So, let's try to get some space here because I still want to be able to look at this tree. Okay, so for df dr, this is going to be equal to, we want to go from f down to r. So here's one path that will get us that. Okay, so we know that it's going to include df dx times dx dr, or partial of x with respect to r. But there's nothing that passes through y that ends in an r here, so we're not really going to have anything else. This is just going to be our only term in this particular part. So all we have to do is find the partial with respect to x, partial with respect to r of x. And we already computed df dx, and that's going to be equal to 3x squared. And then partial of x with respect to r is equal to 2rs. All we got to do is plug these two pieces in right there, and that will give us our answer. So we'll have 3x squared times 2rs. And we had said earlier that x is equal to r squared s, so I'm going to make that substitution here. So we'll have 3 times r squared s squared times 2rs, and that's going to give me 6r to the 5th s cubed for df dr. Okay. Oops. And so that's pretty much all there is to that part right there. We also want to find df dt. And if we look back here at our diagram, again, starting here at f, if we go down through x, there's nothing that depends on t here. So the only path we're going to wind up with is f to y and then to t, like so. And in this scenario, that means we're just going to have df dy times dy dt. So df dy, that was equal to 2y, and then dy dt, oops, dt, y was equal to s squared t, so we're just going to have s squared as being that partial derivative. So now all we got to do is plug these two pieces into here. So we're going to get 2y times s squared, and y is, again, equal to s squared times t. So I'm going to get 2 times s squared times t times s squared, and that's just going to give me 2s to the 4th t for df dt. So pretty straightforward. That diagram is super, super helpful when we're wanting to work with the full-blown chain rule. Again, the idea here with the multivariable chain rule is that you just want to be able to account for all the different possible dependencies here, and drawing this tree really helps you keep track of how we put those together. Now, there is kind of an alternative way to approach this, and this would be to substitute first, although this doesn't always work out too well. But in this case, it really does. And this is a really great way to check your work to make sure that you did everything correctly. So in this example, we had f of xy was equal to x cubed plus y squared, and x was equal to r squared s, y was equal to s squared t. So if I want to, I can just swap out, when I say substitute first, I mean just swap out the x for what it is equal to and swap out the y for what that's equal to, and then just simply take the partial derivatives from there. So if I wanted to take f of r and t, f of r, s, and t, instead of just being in terms of x and y, I would get r squared s cubed plus s squared t squared. So that would be r to the 6x cubed plus s to the 4th t squared. Okay. So now at this point, in order to find, say, df ds, for example, all I would have to do is take the partial derivative of this now directly instead of using our chain rule and the tree and all of that stuff. So df ds, we're going to get 3 r to the 6th s squared plus 4s to the 4th, third t squared. And if we look back at our original answer that we got earlier, they do indeed agree. So the point of this here is that you can use either the chain rule in this scenario or plug in the values first, or the other variables first, and then take that partial derivative. Similarly, df dr, we just take the partial with respect to r. We get 6r to the 5th s cubed. This piece drops off because there's no r in it. And then same idea for if we want to take the partial with respect to t. And we're going to get 2s to the 4th t for that one, which also agrees with our previous answer. Okay, so anyway, the idea behind this is that you can do it either way if the problem allows, although I will say sometimes it's really kind of messy to try to plug these things in first, and the chain rule might be your best bet. Or, you know, vice versa. This was a lot simpler than the other one, but it's really helpful to be able to try them both ways to see how they work together. Now, one thing that I do want to kind of point out, just to kind of ground this process for you a little bit, is that you should notice that a single path is actually really quite similar to when we worked with the chain rule for a single variable. Okay, so our single variable chain rule said that if we had f with another function plugged into it, and we wanted to take its derivative, then we take the derivative of that outside function with the inside function still plugged in, and then we take the derivative of the inside function, like so. Now, if we want to look back at one of our single chains here that we had back on this diagram, say f to dx, df dx, and then dx dr, this corresponded to our partial of f with respect to r, and this had been equal to the partial of f with respect to x times the partial of x with respect to r. And you can kind of think about this partial with respect of f with respect to x as being the derivative of your outside function, which would be kind of like f, with your inside function plugged in, which is kind of like x, and then the derivative of your inside function with respect to the very inside variable, which was r, right? So x here is kind of acting like that inside function in f, and then r is kind of like that very final variable there. So anytime that you're looking at just like a single path on that tree, you're just looking at working with the single variable chain rule. And then when you're looking at multiple paths, you're just applying this same idea to one path at a time and then adding them all back up. Let's do one more example, or at least one that looks like this anyway. I'm going to do one with 3 variables. So we're going to have f of x, y, z is equal to z cosine of x squared plus y, where x is equal to sine of t, y is equal to s to the 4th, and z is equal to st squared. And in this situation, we are going to find the partial of f with respect to s and the partial of f with respect to t. Okay, so I always like to start with drawing that tree. So I have f of x, y, z. And now this time, f is dependent on 3 variables. So x, y, z. In this scenario, x is only dependent on t. Y is only dependent on s. And z is dependent on both s and t. So if we want, we can kind of interpret this as being a change in f is dependent on a change in x. So that's df dx. And then change in x is dependent on change in t. So dx dt, or partial of x with respect to t. Same idea here with y. Change in f is dependent on a change in y. So df dy corresponds to that leg. And then dy ds corresponds to this leg right here, because a change in y had to come from a change in s. We can apply the same idea on this third leg. Df dz for this part right here, or partial of f with respect to partial of f with respect to z, partial of z with respect to t, and then partial of z with respect to s. Okay. So let's first find df ds. Okay. So df ds, the only things that trace from f down to s have to pass through y and z. So we'll have this path here, and then this path here. This first path here is df dy, or partial of f with respect to y, times partial of y with respect to s. And then we're adding to it this path here. So that's going to be partial of f with respect to z times the partial of z with respect to s. So now we just have to compute each of these 4 parts, multiply them together, add them together, and that will be that. So let's see here, partial of y with, or partial of f with respect to y. That's going to be, looking back up here, we're going to take this with respect to y. That's going to give me negative z sine of x squared plus y. And then if I take the partial of y with respect to s, that is going to give me just 4s cubed. Now I want to look at partial of f with respect to z. And I'm going to get this cosine x squared plus y is just basically a constant because we're not worried about the x and the y. So the z is going to go away, and we're just going to be left with cosine x squared plus y. And then partial of z with respect to s is going to give me just t squared. Okay, so now at this point, all I got to do is plug these pieces back up into here. So partial of f with respect to s, that's going to give me negative z sine of x squared plus y, and then times partial of y with respect to s, 4s cubed, and then I'm adding to it this next piece here, cosine of x squared plus y, and then times t squared. Okay, so now at this point, what we're able to do is go ahead and swap these out, the z, x, y, out for their independent variables, what they're related to, and I'm going to get negative st squared sine of sine squared t for x, and then plus s to the fourth times 4s cubed, and then I'm adding to this cosine of x squared is going to be sine squared t plus s to the fourth, and then just times t squared. I can kind of rearrange this a little bit just to clean it up. I'm going to get negative 4s to the fourth t squared sine squared of t, and then plus s to the fourth, and then outside of that plus cosine of sine squared of t plus s to the fourth t squared. Or I can bring the t squared up here. It doesn't really matter either way. All right. So that was df ds. Let's do df dt next. All right. So df dt. Looking at this diagram here, I'm going to want to go from f down to t, or over here as well. So first we have this one right here. So that's going to be equal to partial of f with respect to x times partial of x with respect to t. And then we are adding to it this other path here, like so. We're going to get df dz times dz dt. Okay. So I just need the partial of f with respect to x, which is we're going to look at this right here. We're going to have to apply the chain rule. We're going to get negative z sine of x squared plus y, and then we have to multiply by the derivative of x squared, so it's going to give me 2x. And then I want partial of x with respect to t. That's going to give me cosine of t. And then I need partial of f with respect to z. Well, we already found that. We said that that was cosine of x squared plus y. And then now I need partial of z with respect to t this time. And that's going to give me 2st. Okay. So this is all the pieces that I need to be able to fill this out. So partial of f with respect to t is going to give me, let's see here, we've got negative z sine of x squared plus y times 2x times cosine of t, and then we add to it this cosine of x squared plus y times 2st. Okay, so now at this point, I just want to plug in my independent variables. So z, we had said, was equal to st squared, so I'm going to have negative st squared sine of sine squared t plus s to the fourth times 2 sine of t and then cosine of t plus cosine of sine squared t plus s to the fourth and then 2st. I can rearrange this a little bit, but really there's not too terribly much that we can do to clean this up. I guess I can bring this negative 2 out to the front, and then we have st squared sine of sine squared t plus s to the fourth, and then sine of t times cosine of t. And then add to it 2st cosine of sine squared t plus s to the fourth. And that's pretty much all there is to this piece right here. Of course, if you want to check your work, you're more than welcome to, and in fact, I encourage it to plug these values here into here, and then take your partial derivatives using the chain rule the way that you normally would. So I'm not going to show that here. I'll leave that to you, but again, that's something that I really encourage, and sometimes problems actually request that you show it both ways. So something to try out for sure. All right, so I wanted to do one more example of showing how to compute the like the norm of a gradient, for example, when we're working with polar coordinates. So suppose that we're given the formula. We're told that the norm of the gradient of a function u squared is equal to the partial of u with respect to r squared plus 1 over r squared partial of u with respect to theta squared. And this is, u is a function of r and theta. Okay, so in this scenario right here, if we're given a function, say u of r theta is equal to e to r cubed sine cubed theta, we're able to take this here and be able to figure out what the length of the gradient is without having to actually compute the gradient. We can just find these partial derivatives, plug them into here, and then that pretty much gives it to us. So to be able to do this, let's go ahead and start with partial with respect to r. That's going to give me 3r squared sine cubed theta, e to the r cubed sine cubed theta. And then if I wanted to take partial with respect to theta, we're going to have to apply the chain rule, I guess, twice, because theta is inside of sine cubed, which is inside of an exponential function. So doing that, we're going to take the derivative of what's up here, and that's actually going to be r cubed times 3 sine squared theta, and then we have to take the derivative of the sine here because of the chain rule, because sine is inside of a cubic function. So cosine theta there, and then we still have e to the r cubed sine theta, and that's cubed too. Okay. Let me clean that up just a little bit. 3r cubed sine squared theta cosine theta e to the r cubed sine cubed theta. All right, great. So we have our two partial derivatives, u theta and ur, and now all I've got to do is plug these two expressions into here, and that gives us a way to get the norm of the gradient. So this is going to be equal to this piece here squared. Plus 1 over r squared times all of this squared, so 3r cubed sine squared theta cosine theta e to the r cubed sine cubed theta squared. Okay, so I'm going to go ahead and distribute the squareds to both of those pieces here. We get 9r to the 4th sine to the 6th theta e to the, and this becomes 2r cubed sine cubed theta, and then plus 1 over r squared, 9r to the 6th sine to the 4th theta cosine squared theta, and then e to the r cubed sine cubed theta, and this is actually times 2. Okay. So this is one reason that, I mean, for one of many reasons that it is really, really important that you are very familiar with your trig identities, because a lot of times it's really easy to take a look at this and be like, okay, I really can't do anything else except, okay, maybe I can cancel out the r squared and the r to the 6th. But if you're thinking, okay, what kind of trig identities could I use? What kind of how could I introduce that to be able to simplify this down a little bit farther? You'll notice that there's a sine to the 4th here. There will be a 9r to the 4th here once this is simplified down. There's a 9r to the 4th here, and there's a sine to the 6th here, and then this is on both of them too. Which means that if we're able to factor out the right stuff, we're left with just sine squared theta and cosine squared theta, which is equal to 1. So we're going to go ahead and do that, and it's going to clean up our expression a ton. So what we get as a result is 9r to the 4th sine to the 4th theta e to the 2r cubed sine cubed theta. Okay, so I pulled out these two cancel. I pulled out the 9, the r to the 4th that's left here, the sine to the 4th that's here, this guy here, and then a sine to the 4th from there too. And we're just left with, this guy leaves a sine squared theta, and this guy leaves a cosine squared theta. Okay, so, well, that's just equal to 1. So all we're left with is 9r to the 4th sine to the 4th theta e to the 2r to the 3rd sine to the 3rd theta. And that is pretty much our answer right there. It's a lot nicer than the way all that looked. Now, I do want to kind of highlight that we could compute the gradients using Cartesian coordinates, and we'll wind up with the same answer. So our goal is to find another expression for the length of the gradients of u squared, and we're going to use Cartesian coordinates to do this. So our function was u r theta is equal to e to the r cubed sine cubed theta, and to convert these to Cartesian coordinates, recall that x is equal to r cosine of theta, y is equal to r sine of theta, and we're going to use these to substitute in for here. So if we want u to be in terms of x and y, I'm going to take e, and r cubed sine cubed theta is just r sine theta, all of that cubed, so that's just going to be y cubed. So to get my gradients, well, I need the partial with respect to x in the first component, and that's just going to be 0 because there's no x's in that equation. And then I need my partial with respect to y in my second component, and that's going to give me 3y squared e to the y cubed. Okay. So what this means, to get the norm of u squared, well, that's just going to be the square root of 0 squared plus 3y squared e to the y cubed squared. And then all of this is squared. So I guess that cancels out the square root. And I'm just left with 3, oops, that should be a 9 y to the 4th, e to the 2y cubed. Okay. Well, let's work a little bit backwards here and go back to r and theta, since that's what we had started with. So if I substitute in r sine theta anywhere I see a y, I'm going to get 9 r sine theta raised to the 4th, e to the 2 times r sine theta raised to the 3rd, which is just equal to 9 r to the 4th sine to the 4th theta, e to the 2r cubed sine cubed theta. And that is exactly the same as what we got computing our gradients using our formula up here. So I guess the main idea behind this is just that a lot of times there's a couple of different ways to approach these problems. A lot of times you can pick whichever one works best unless you know the problem tells you otherwise, in which cases, I don't know, a lot of them ask you to do both. But anyway, that's how you generalize using the chain rule to working in higher dimensions. Hopefully this has been helpful, and I will see you next time.